Okay, we are into the meat of Unit 4 right now. U4A3 is equilibrium problems. Folks, this part is so sort of big and important that we're going to need 3 videos to do U4A3. I would suggest you watch these videos several times, try and follow the bouncing ball, get out to YouTube, take a look, be ready to settle in and take some time with this. Have organized notes for the test so that you can go back through this and figure it out. What we have here for our first example is we have an equilibrium situation. So remember, to have equilibrium, we need a closed system. So basically means you need a stopper on it. You have ethane gas, C2H6, and it's breaking down to form hydrogen gas and ethene. And then that goes back to form ethane in a equilibrium situation. Let's say that all we did was we pumped ethane into this system. So we have nothing to begin with in here, and then we pump ethane in. So if this represents the concentration, and this is the symbol for concentration of ethane, it's very high. At the beginning, we will have no ethene or H2. Its concentration will be low. As these two start to react, the ethane is used up to make the ethene, and we know we reach an equilibrium when the graph starts to flatline. That means we have an equilibrium. In this equilibrium, we have more ethane than we do ethene. That means we're going to have a K value of less than 1, and I'm just going to make a number up there. And you don't know what that means right now, but that's where we're going to go next, is to figure out what that K value means. K value is determined by taking the products over the reactants. So I take my concentration of H2, concentration, square brackets, of H2, multiplied by my concentration of C2H4, and I divide it by my concentration of C2H6. If my number is large, so if the K value I determine is large, greater than 1, that means when we've reached equilibrium, we're going to have more products than we are reactants. If my K value is small, less than 1, so like in this case here, it means that my reactant side is favored. As in this graph, I would have more ethane. Than I would have ethene. I better write that again. That is ethene. Okay. A couple of points here. Let's say that we have a solid somewhere in this reaction. These are all gases, but if something was a solid, let's say the H2 was a solid, we would leave it out of the determination. Solids are not used in equilibrium determinations. Next point, if we have a coefficient. So let's erase this and write this out again. If there was 2H2, then in this reaction, we'd have to put a 2 up here. So we'd have to square the concentration of H2. If we had a 3 here, we would have to put a 3 here. Okay, so make sure you understand that as we go along. Let's jump in the deep end. We're going to try 2 questions and see how it goes. Let's say we have 2 moles of A and 2 moles of B in a flask to begin with. Remember, this is what our situation looks like right there. We're going to put 2 moles of A and 2 moles of B in a 2-liter flask. How much C would we have at equilibrium? So what we're asking here is something similar to this. We put ethane in a flask. How much ethene would we make? Well, first of all, everything has to be in concentration. So we have to take our moles and we have to divide it by our liters. That's concentration. If they give you a volume of 1 liter, then whatever moles you have is going to be your concentration. 2 divided by 2, 2 moles divided by 2 liters is 1. For B, 2 moles divided by 2 liters is 1. If they don't tell you that you have something, then you've got 0. So what they're saying here is that they've got a flask and they've pumped 1 mole per liter of A and 1 mole per liter of B into a flask. Now what happens is these react. So we take from our reactant side and we add to our product side. Okay, so this here chart is going to make up an algebraic formula for us that we can use. But what the second line tells you is what are you taking away and what are you adding? You can only add to the side you have nothing. You can only take away from the side where you have something. Now, let's say that we had a coefficient of 2 here. This would become 2x. So anywhere you have a coefficient, that goes in front of the x. We do not have a coefficient. We'll get rid of that. To find out what you're going to have at equilibrium, read down the line. 1 minus x. 1 minus x. 0 plus x is x. Your formula is K is equal to products over reactants. Hey, see this K value here of 10? It's greater than 1. That means when we do reach equilibrium, we're going to have more of C than we will of A and B. So watch for that. It's products over reactants. That would equal 10. And I wrote this backwards. Hey folks, I'm going to do something here in this problem and just bear with me. I want to do this to show you something. Let's imagine that we did have a 2 out there in front of the C. So what we'd have here is 2x, 2x. I'm going to write a 2x in here and then we're going to square it. Remember, if you have a coefficient, then it's got to go up here also. Now, the reason I'm doing this is to show you what's happening when you do have a coefficient. You have a square on the top, you've got a square on the bottom. We can see a square in two different ways. We can see it because we can actually see a squared sign, or we can have two things that are the same. If you have a square on the top and bottom, take the square root of everything. And this will simplify. And what I'm going to do in the next video is I'm going to show you what we do when we don't have a square. So the square root of 2x squared is 2x. The square root of 1 minus x times 1 minus x is 1 minus x. And the square root of 10 is 3.2. Now I rearrange the formula. I'm going to bring this up over here. 3.2 times 1 minus x equals 2x. 3.2 minus 3.2x equals 2x. I'm going to bring the negative 3.2x over. 3.2 equals 5.2x. X equals 3.2 over 5.2. And that equals about 0.61. If you want to know what you have at equilibrium, take your 0.61 and put it in all of these formulas. So you're going to have 0.39, because that's 1.61, 0.39, and 1.22. So that's just 2 times 0.61. All we've done here is shown you what you're going to have at equilibrium in the products and the reactants. And I said because the K value is greater than 1, you'll have more products than reactants. In this case here, we don't know the K value. Let's try and find it, but we're given this information. We're told that we've got 1 mole per liter of A at the beginning, 2 moles per liter of B at the beginning, C we have 0, and once we reach equilibrium, we have 0.5 here. So if we set up our algebraic formula, we're going to lose from this side, we're going to gain from this side. Now remember, what we're being told here is what we've got at the beginning and what we have at the very end of this one. So if this is 0 plus x is 0.5, x must be 0.5. That means if we subtract 0.5 from 1, this has to be 0.5. If we subtract 2 minus 0.5 here, this has to be 1.5. I'm jumping ahead. Let's back that up. We know x is equal to 0.5 because 0 plus x was 0.5. Therefore, x equals 0.5. If x is equal to 0.5, 2 minus 0.5 is 1.5, and 1 minus 0.5 is 0.5. To find our k value, products over reactants equals 0.5 over 0.5 times 1.5. And I think this comes out to about 0.6. I think it does. Anyways, there's different ways we can use this thing called I call it an ice chart. I call it ice change equilibrium. They call it ice initial reaction equilibrium. Anyways, to use this chart, we can put different information in, and then we can do algebraic manipulations. Guys, this is part 1. In part 2, I'm going to show you what to do when we don't have a perfect square when we do a calculation.